Hello, so we're just about to start the next session before lunch. So you had, we were told that there's no free lunch for machine learning, but luckily I think you do get a free lunch today. So that's the good news. So we got the different steps of the machine learning that our framework that I'm going to be going through. And I'm going to talk about what goes in and what comes out of the PLP. And then also at the end of this, we're going to show you a connection to get onto Amazon servers. We can actually have a play around, and during lunch I'm going to set up some slides and you can actually see. So at the end there will actually be some demo code up, so you can actually play around with the objects that we have out rather than just seeing some of the illustrations we have. So our five-step framework, we have to specify the problem, which the good news is you've already done this, so I can skim through this pretty quickly. You mentioned it all when you came up with your prediction problem earlier. But I will say there are some considerations you want to make that are overview for that. Then there's going to be the suitable data, so you need to make sure you actually have data for your prediction problem. Select the predictor variables, and I'll talk about what we have in the package, what you can add in. And then the models, the same thing, what we have, what you can add. And then we'll talk about how we actually do the validation, and I'll show you some examples of that. So you all saw how you do the prediction problem. We want it to be well-defined, so it's transparent. Your T, who it is you want to do the prediction for, your O, what it is you want to predict, and your time at risk, when you're going to be predicting the outcome occurring. But I will say that a lot of the times when you're doing a prediction, the key thing is to make sure that your date that you're pivoting everything on, so the date where you're looking at to construct your features using the historical data, and the date where you're actually going to be doing the prediction of the outcome afterwards, is very key. And if you want to make this clinically useful, you need to make sure you have a date where it's going to be useful for the clinical application. So it might be that if you know a patient's going to begin to a doctor for a set point in time, that might be the good point in time to actually do your prediction on, because they're going to be interacting with their doctor at that point. So if they go in and they have some sort of drug, as we see in the examples here, that could be a good pivot for your prediction. Because when you have the drug and you see your doctor, that's when they can do the prediction. If you pick a point in time where it's not really well defined when they're going to be interacting with their clinician, then it might be harder to actually implement this model. So that's one consideration that I would say that I see a lot when I'm doing predictions for work that I want to actually consider. And then the suitable data. So we said that we got a lot of data in OHDSI. So there's lots that you can actually do for validation if you get other people to run, if you don't have the data yourself. But the problem is that sometimes there might not be data for your prediction problem. We saw earlier when we were going through the examples, some of the outcomes could be very rare. Some of the target populations could be hard to define with our data. We don't have smoking well defined. Some sites might, but they might not have it in the way that you want it. So that is one consideration when you're doing models. You need to make sure that it is actually suitable for the data you've got. Or that's available if you're going to be able to collaborate. And then the predictor variables. So we've actually tried to standardize this so that it would be easy to share the models. But you can actually add your own predictors if you want. You can write the code and share that and get people to run it. But the one of the main things I think that was probably limiting the ability to reproduce people's models was maybe in the construction of the predictor variables. Because one, you might not have it in your data set, which then how do you implement someone's model if you don't have most of the predictors they're using? It's very difficult. And two, it's not always clear how people are constructing predictors. So we wanted to make it so that it was very clear how we're going to construct the features, the predictors, so that it would be easy to reproduce across the different data sets. So what predictors do we have at the moment? Well, we saw this picture that Peter put up earlier, and we see that generally our prediction problem, you have some index time, so this is indexed on the treatment, and that's the person time is 0. And then you look back, and you've got conditions, drugs, devices, procedures, measurements. All of these are in the CDM that we work on. So you can have features for all of those records. And the nice thing is with our standardized features, you can actually pick 3 different time periods to look at. So you've got your short-term, medium-term, long-term, or any time prior. And these are flexible, so you could say, I want to look at conditions that occurred in the short term, and I'm going to define my short term at my index date of 0 all the way to a year, 30 days prior. But you could also say, I want to look at, say, 5 days prior. And the same with the medium and long term. These are actually flexible. The default's 30 days in the short term, median term is 180, long term is 365, but you can play around with that. Or you can just say, I'm going to look at the records, any conditions, drugs, devices, procedures, measurements they have ever in the history. So we've actually got quite a lot of flexibility in terms of the temporal nature of these. And you have the demographics. So I've not illustrated it here, but you have the demographics at the 0 point in time. So their age, when they had that treatment, and all the different, the gender is kind of not temporal, so that kind of stays constant. But anything that is temporal, for the demographics, it will be at the point 0 in time. And then you've got your models. So we've got a lot of machine learning models put into the package right now. And we have the whole process of doing it, which I'll just go through some of the considerations that you need to make. But the nice thing I want to stress is that this framework that we've got, you can add in your own models. So if you're not happy with the models we have for your specific problem, maybe you want to have some sort of feature engineering done before, maybe you want to add some new model that's just come out and you want to test it, you can actually plug that in quite readily into the framework. And it could be nice if you're someone who's developing models, this is a great way to actually test out your methodology. You can add it to the framework, you can create a package, and you can get the whole community to run it and actually see how well it does. And because we have the existing models, you've got benchmark comparisons as well. So for model development, the framework could be very handy.
So may I add one thing here, that our question is that there's this proposal by Mark van der Laan on the super learner. Do you consider including that? That may be an obvious one to include.
Yes.
Is an ensemble learning? Yeah.
So we've actually got we've built that in. We haven't really done any studies with that. Have you actually done any studies for that yet, or?
Yeah, so we actually had a poster for that. We looked at ensemble training. And it's very interesting to look at it, maybe also for transportability assessment. Okay.
Yeah.
So we can combine each of the individual models and then use a super learning and conscious regression on top of that, and then weight the individual models in different ways. Okay.
Yeah, so what I would like to see is, with the super learner, my gut feeling is that you need to have a lot of data because you've obviously got to have that extra layer of training the super learner. And then it probably won't be apparent that it's good until you try it on lots of different prediction problems. I think it should improve consistency, but it might not be good for an individual. So I think it would be interesting to see if we did the replication of the 21 outcomes, if it actually improved then. But I think as a one problem, you might do it once and see it doesn't really have much improvement, and I don't think we should be discouraged by that. So what models are currently in the package? We have lasso logistic regression, gradient boosting, random forest, ADA boost. So we have lots of different boosting bagging. We have the decision tree if you want to go just to the individual tree rather than do any of the boosting or bagging with the trees. We don't have non-tree boosting, but that is actually something that people could add if they wanted that. We have the neural network and the deep learning. The deep learning is slightly different because we have temporal features in that case. So that's going to be slightly different than most of the other classifiers we're using. Your standardized features are actually going to be a bit different. We have k-nearest neighbors, but that's a bit difficult because you can't share it easily. So if you're doing a model on your site, k-nearest neighbors could be a good model to use, but it's not obvious how you'd actually share that across the collaboration because the k-nearest neighbors, the data is the model. So it's hard to share. And then you've got naive Bayes, but generally we found this hasn't performed all that well when we've actually been looking at that. So that's one that we don't actually tend to use much, but it's in there for a comparison anyway. And you can add your custom model. So if there is something that you wanted to add, you can plug it into the framework and you can actually see how it's doing. Now I'm just going to talk a little bit about the machine learning training process. So as Peter mentioned earlier, there's no free lunch theorem. The way that a model works is effectively, if you thought about having two predictors in your problem, you're trying, and you have two classes, we're doing binary classification. If you looked at plotting the classes by measurement 1 by measurement 2, and then you colored in the first class, say if you had the outcome, you're red, and if you didn't have the outcome, you're green. Then what you're doing when you're learning a prediction model is effectively just identifying this decision boundary. So you're just trying to find a function that tries to separate the two classes as much as possible. And the decision boundary is going to differ between all the different classifiers you're using. So decision tree can only go up and down. You can only, so you can see here, you've got some straight lines for your decision boundary. You've got different ways of doing it for SVM and neural network, and random forest is more fuzzy because you're combining all those decision trees together. So because they have different ways of doing the decision tree, this is why you have the no free lunch. It all depends on how your data are. If your data are spread out in certain ways, you might find the decision tree works well with the ups and downs. But in other ways, you might need to have something that's got more flexibility. So it all depends on your data, which model is going to be best. And this is why we recommend apply every model that you can. You also have hyperparameters. So when you're training model, you have the parameters of the model, and you have the hyperparameters. And the hyperparameters is effectively, they control the complexity of the model. So if you think about it in terms of a neural network, your parameters that you're trying to train at the end is actually the weights for each of between the different nodes. But the hyperparameters are the number of nodes you have and the number of layers you have. So you can have a very simple neural network, and you can have a very complex neural network. And the hyperparameters are the number of nodes and the number of hidden layers that you have. So they actually effectively control the complexity, and that again depends on your data. If you've got data that's very easy to separate, you want a very simple model so you don't overfit. If you've got data that's all over the place, then you need a very complex model. And you see here that as you increase your hyperparameters as you make your hyperparameters more complex for your problem, you can actually get perfect performance on your training data because your model's so complex. It's easy to do the prediction. It's such a complex model. But you're going to do poorly when you perform it when you apply it to the left-out data because it's not going to generalize. It's going to do perfect for your development data, terrible for your holdout data, and that's overfitting. And if you have a simple model, you might find that it's too simple that it can't actually learn to separate things, and then you're going to have poor performance for both. And just to give you an illustration of this, you can see here that if you have the situation again when you've got two features because it's easier to visualize, and you have the x's are one class and the zeros are another class, if you tried a linear model, so in this case the hyperparameter could be, if this is a polynomial, hyperparameter could be n. So a linear would be n equals 1. You've got, it's too simple a model to actually be able to discriminate and separate these pots. You wouldn't be able to get the dots and the crosses separated with any linear model. And this is underfitting. But if you had a polynomial where n equals 2, approximately, then you could actually get a nice curve around it, and you could actually separate most of the dots from the x's. And this is actually doing pretty good for what you want. But if you had a polynomial of, say, 20, you could just go all around all the different dots and the x's, and you can perfectly discriminate. And it's going to be fantastic for the development data set that you're using, because on your development data set, it's perfect discriminating. It's separating those classes perfectly. But when you try and generalize it, you might get a new dot here. If you get a new dot there, it's probably actually, well, it would be like a class dot. But because you've gone onto that first x and you've kind of overfitted to that x, it's going to predict it as an x group instead. So that's not an ideal situation. This is what the hyperparameters are basically going to do when you try and find the hyperparameters. Depending on your data set, it's going to find which sort of complexity is good for your problem. And then the final bit is how you validate the model. So we mentioned earlier we have two types of validation. You have the person split and the train split. So with a person split, if you had 16 people in your development data set, and you wanted to hold out 25% to do the validation and train on 75%, then you'd want 4 people in your test set. So for the person split, you just randomly pick 4 rows. So we see here we've got 4 rows that are in yellow, and that's your test set, and the rest are in the blue. That's your train set. For the time split, you want to do it where you're using older data in your test set and in your train set, and newer data in your test set. So we can actually look at the last 4 people in these rows were July 2016, February 2016, February 2014, and March 2012. So those 4 people go into your test set, and you're going to use those to actually evaluate the model. And this can see whether the model's able to actually do a prediction in a later point in time using the older data, because when you're developing a model, you're actually going to be applying it to data in the future. So this is a more realistic evaluation of how well the model's going to do, and it can tell you if there's temporal changes that might impact your performance when you're applying your model. And then finally, we've got the external validation, which we can do very well as a community because we can share our models. As you saw yesterday, we were able to put the model on GitHub. 6 different sites downloaded the data, the model, applied it to their data, and we got the external validation within 1 hour compared to the 3 years that it normally takes. So using the framework and the collaboration, we can do very extensive external validation. And this will tell you whether the model transports to different data sets and just give you more insight. Are there any questions at this point?
So does the package have support for multiple index times and multiple predictions per patient? And if it does, how does that interact with temporal partition of the data set?
So having the same person with twice.
Right. They qualify twice, right?
You can have them. So generally when I'm doing a prediction, I will make it so that they never overlap in their covariates time. So if you have one person, and I was going to say a year's worth of history, I would make sure they didn't occur within 6 months of each other because I don't want them to be correlated. The package would do it. It would do it without any sort of, it wouldn't fix the issue that's going to occur from it. It would just assume that they're different, independent, which would be wrong. So we don't have the support to do it correctly. But you could have multiple people in there for the prediction, and it would just assume they're independent.
Just a follow-up, this question. If we have some data set of time series, like the vital signs, blood pressure keep changing, the trend of for example, patient blood pressure keep dropping, so it may predict the mortality of the patients. So how we can put those information in the model?
So there is the deep learning now, which has the temporal features. So you can actually have it where rather than just having the static time and looking at set time periods in the past, you can say in the last week, we can go in weekly intervals for the last X amount of years or so. And then you can do some sort of model in the deep learning model. Otherwise, if you wanted to do one of the standard classifiers, you would have to somehow aggregate that into some sort of time period feature. So you could say what was the average of these measurements over some time periods. And you would have to do some custom covariates for that, because we don't really do any averages and stuff at the moment.
So a follow-up to that, for databases like the Optimum Panther, where there's a lot of really interesting granular EHR data, does the current sort of feature engineering package incorporate some of those vital sign measures, laboratory results, or is it more just the fact that an assessment was made is used as a potential predictor?
Yeah, so right now feature extraction does add some of the measurement values that it's not. So there are some non-binary values in feature extraction, but they're very basic. So it will say you can say either did they have a measurement, yes or no. Then there is one like did they have a measurement. I think it will have the measurement value, and then it will be is the measurement above or below the expected value if we have the expected value in some information. And that's pretty much all that feature extraction will do. But you can create custom covariates to do whatever you want. So if you wanted to have some other aggregate of the values or something, you could create that. But it just wouldn't, it would be a little bit extra work.
Any examples of community validation, and where there's a regional model that's suggesting other environments, and then some kind of presentation of that one could look at to see how that works and that cycles in the model?
So in terms of this community or like the general prediction community? So I think in the general prediction community, there's been models like the CHADS. You'll find external validation all over the place, and there will be comparisons of the external validation for CHADS. And then there is actually papers that are saying, like some of the, I think the progress report did actually state some of the considerations, like you shouldn't really do external validation if you have a low outcome count. So they did say some stuff, but I think because we're changing the way external validation is done, so in OHDSI we can do it so efficiently, I think there's going to be a lot of research questions coming out of how best to do it, what do we like. So for example, one question I've had before is if you do an external validation for a model, and your model got an error under curve of 0.8 in your data, and then the error under curve changes in all the other data sets, does that mean it's a bad model? So if it went to 0.6 in other data sets, is that a bad model? And it's hard to know whether it's because they don't have the variables that you need for your model, or whether it's you overfit in your data. I mean, if you have the internal validation, you should be able to have some insight into overfitting, but you might have something in your data set or you might have done some process wrong. Hopefully not if you're using the framework because we standardized it. But yeah, I think there's going to be a lot of questions on that. There were 2 studies, I think, this year in OHDSI with the external validation. So I think Claire presented one where she applied the existing models for bleeding risk, and then she did the PLP for that and validated that across the J&J data sets. And that kind of gave us some insight. But I don't know if she really mentioned too much about the process. It was more just the results. And I think there was another one for the CHADS, applying the CHADS on all the different data sets as well. I guess the lesson learned most of the time is the cohorts. If you're doing external validation, a lot of the time the cohorts might only work for one site and not for other sites. But we haven't got anything published really to talk about that.
For example, we submit a job. For example, if I submit a job to run the query, for example, for a neural network model, how long it generally will take to get a response or get a result?
So it all depends really on the size of your data and the hyperparameter search you do. So a lot of the time, so some of the models like random forest and gradient boosted machine, I'm quite relaxed with their grid search. I know there's general ideas of like random forest, it's the square root of the number of features is your go-to start for mTry. So for those ones, I won't do a big grid search, and it'll be pretty quick to return, unless you've got millions of patients, and then it could take a few hours. But then it also depends on your computer system. So I'm assuming I've got 100 gigs of RAM and a good CPU, and that would be pretty quick for most of the trees, unless it's a million patients. But if you do a big grid search, if you really wanted to find the optimal hyperparameters, especially with the neural networks where there's a lot more hyperparameters to tune, then it could take a long, long time. So it depends really on your design. I would say as an initial thing, I just put in a very quick search just to see what's the feasibility of it, because the hyperparameters probably aren't going to make much of a difference, especially with the tree ones. Maybe with neural networks a bit more, but with the tree ones, you get a ballpark figure. If it's poor, I'm not going to waste too much time tuning it. But if it's promising, then you might want to spend more time.
Okay, thank you.
So yeah, I have a question about overfitting. So yesterday I saw a poster from Peter's team, actually. So the study is about predicting the heart failure. The prevalence is about 2% and using 3 data sets across. So I have a question because there is a figure shows how the data and the sample size increase, how the sample size will affect the model performance. Actually, I find the AUC in the training data set is about 0.8, and in the testing data, the AUC is about 0.9. Actually, both are very good. But to me, I feel like you still have an overfitting problem, because 0.8 and 0.9 to me is still different a lot in terms of AUC. So and the figure shows when the sample size is increasing from 50,000 to 150,000, there's no change. I mean, the trend are the same. So they tested across 3 data sets have very similar trend. And in the data set, in the model, they put like 90,000 features into the model at the very beginning, and used the 3 methods. One is the logistic regression. The second, the left 2 are the tree-based. So even we choose different method and different data set and also different sample size, the overfitting problem is still not solved. So this is very interesting actually. So yesterday I asked Frank Harrell. So he suggested maybe you should a solution. Maybe you choose another performance metric. For example, like a golden standard likelihood method, like including the pseudo R-square. This sounds like a solution. Like you should choose different performance metric, like the AUC you are using and the PR. But he is suggesting using R-square maybe to to solve the overfitting problem. So I don't know. So I just want to, discussing about this. So.
Yes, that's interesting. So I didn't actually see the poster. So, but yeah, because I would have thought that it would have converged as you got more data. There should have been less overfitting. I'm wondering whether the models just had, with the more outcomes, they were including more covariates maybe into the models. So that they were even though you had more data, it was still overfitting because it was just adding more information. So normally the lasso, for example, I found generally with the models that we do, if you divide the number of outcomes by 10, which is the rule which people always go to, that's how many variables the lasso fits, roughly. So I think if you added more outcomes, I would guess the lasso would fit more covariates. And then because it's got more covariates, even though you've got more data, it might still overfit. So it might get to a certain point where you don't need any more covariates for your model. There's nothing else that's kind of predictive. And then maybe it would converge a little bit. So maybe we just never reached that far enough. It could be. That's one far.
So Peter, it was your poster, right?
Just a quick question. So in terms of the model currently you have, or maybe in the development, can be accommodated, predict the outcome, repeat the measurement. For example, hemoglobin A1C greater than 6.5, patient could be on drug and then lower the level and they high in one period and then they become low next period. Just repeat the measurement of the outcome variable in terms of prediction.
It's possible if you use temporal features. Current temporal feature extraction can extract the exact values from the measurements. So yeah, it's possible. And you can ask me in Korean. My Korean is much better than my
Thank you, Jenna. Good presentation. I have a quick question. From the tool maintenance perspective, I know the package behind the tool are all open results, right? Yeah. So how do we maintain if some package get updated, like the gradient boosting gets one more parameter in the new version, or something like that? How do we manage the communication, in the roadmap, and the traceability, something like that?
So that's a great question. So we're finding with studies that we submitted a year ago on the GitHub, they were using the older version of patient-level prediction. And so if you've installed the newest patient-level prediction, it's really annoying to have to go back. So this is a problem I think we have and we're looking into. Generally, what was suggested to me was just to try and update the GitHub studies that we have with the latest package. And people are looking at, there's a library called Ratpack, that you can kind of have different environments. So we're hoping at some point we'll be able to, sorry? Oh, PackRat. Did I say it the other way, did I? So that library will actually have the environment you need for the study. So it might be that when we do a study, we can put the environment that's needed in there and then use that our library to make sure that you don't have to make any changes to things. But it is very hard when you're updating the package to maintain everything that's dependent on it if there's existing studies. So that's just a very good point that you just need to be aware of. Thank you. Okay, so now I'm going to talk about what goes into PLP and how you actually implement some of the machine learning algorithms. So this is the Atlas interface. This is the latest Atlas that we've got. So this was added about a week ago. And it can now actually do a prediction package from a nice user interface. So if you don't have experience of R, you don't have to worry. You can actually design a prediction now through Atlas, and it will generate an R package. You just have to then put in the connection details. So in Atlas, you're going to be able to play with this in the later sessions today. You're going to have a option on the left-hand side, and if you pick prediction, sorry, that might. Oh, no, it's not. I thought that was my phone. My phone goes off my dog's drugs all the time, so is that my the drug for dog alarm? So on the left side, the hand side, you've got the prediction button. If you click on that, you'll then have the option of creating a new patient-level prediction in the top right-hand corner. And if you click on that, you'll then get this layout where you can give it a name for your prediction problem. You can have a little description if you want to try and remind yourself what you did if you go back in 6 months' time. And then you're going to have options for doing the different prediction design. So you're going to be able to play with this, and it'll be more fun when you actually have it in there. But I wanted to give you this slide with some of the main keys, because you can actually access this PowerPoint. So if you forget what's needed later on, you can go back to this PowerPoint and see these instructions. So you can give it a name, and then the green button will save. If you want to get out of the prediction, if for some reason you don't like what you're doing, you can go to the blue button with the X, and that closes it. And you can also have an option of copying. So if you do a prediction and you want to get another prediction that's very similar to this design, you can actually copy this, just rename it, because it comes up with copy of whatever you've called it right now, and this is not informative normally. So you probably want to rename it, and then you can press the green and save it. So you can easily just expand to new things. And if you want to delete it, you can actually press the red button. I don't generally do that because you pretty want things at the end. And then once you get into this, you have the option of adding your T's and your O's. So we're going away from this 1T, 1O prediction design that most people do. You can actually do as many T's, as many O's as you want. So you're going to create your cohorts, and you can create as many target populations, as many outcomes as you want, and the predictions, the framework will actually do predictions for every combinations of your T's and your O's. You also have the analysis settings. So this is the model settings for your actual predictions. So you can go to the top right where it says plus model settings, and this will give you an option of whether you want a logistic regression, whether you want a random forest, all the different classifiers that we have, and you can select and add that in. So there are lots of different models. This one is the random forest settings. So in the random forest, you have the hyperparameters that you can actually search. And if you want to predict if you want to search lots of hyperparameters, you just put a comma to separate the different values that you want. So for number of trees, the default is 500, but you could put 500, 10, 100, and that will do number of trees. It would search if you had a number of trees of 500, number of trees of 10, and number of trees of 100. And you can do that for many of the hyperparameters. You can also add a logistic regression. That's only got one hyperparameter, then how much you do the regularization. And this is actually an automated search. So the lasso logistic regression, you don't normally have to focus too much on the hyperparameter. Got a multi-layer perception. Again, this has got your number of hidden nodes and some regularization value. And again, you could put different values. So you could put 4, 100, 2 to get different topologies for your network. And the gradient boosting again. So we have lots of different models that you can add in. And you can add in all of these if you want. So you don't have to just pick one. You can pick as many as you want. And then you have your covariate settings. So we've made this a lot nicer than in previous atlases now. So you go to covariate settings. You've actually got a tick box where you can tick which things you want into your models. And as I mentioned before, you have the demographics, and then you have things like the conditions for different time periods. So now you actually have the option of specifying how far back you look when you do your time period. So you've got the long term, which defaults to minus 365 days. You've got your medium term, which defaults to 180, and you've got your short term that defaults to 30, but you can make that flexible. You can make your short term 182 if you wanted. And you can make your long-term 30 if you wanted, but then you just make sure that you're consistent later on where it says long-term for ticking and short-term for ticking. And you can have conditions, drugs, you can have groups. So we use the hierarchy to actually group drugs together into ingredient level, and we group conditions together based on the hierarchies that we have in the vocab. So there are lots of different features. If you select everything, you're probably going to end up with around 200,000 features. So there's going to be a lot of features. And you can pick multiple covariate settings. So it might be you want to look at what would my model do if I just had conditions, what would my model do if I had drugs, how does it improve if I add conditions and drugs, and you can explore all of these questions by picking different covariate settings. And then you've got your population settings. So this is actually where you specify your time at risk. So if you wanted to explore different time at risks, this is where you'd actually go to add in lots of different settings. And your TAR, I've tried to add an illustration here because it's not always very obvious how you define your TAR from these settings. But effectively, your TAR is defined from the variable that says days from cohort start, add exposure days to start, days from cohort start for your end, and add exposure to end. So what this is saying is that if you say your add exposure is no to both of those, everything is relative to your cohort start date. So then you're saying, in this example, 1 day to 365 days from your cohort start date, which we can see in this example I've put up here, where you actually, your task starts from T. For both, the orange lines start from the first part of that rectangle in T, and they kind of, you said 1 day to 365 days, and then from the first one to the last bottom line is your tar period. But if you change that over to actually say add exposure to start, now you're starting at the end of the T box, and that's your tar. So your tar is reduced quite a lot because you're using the amount of cohort, you're using your cohort end period now for your start date. So this is more if you're using something where you might be looking at people who target population who are taking drugs. So if you're taking a drug, you're normally taking it for some time period. So your target population start date will be the start of the drug, and the end date will be once you finish taking that drug. So you can look for the outcome once you finish the drug. Or it might be that you're looking at pregnancy for your target, so you've got a start of your pregnancy and the end of the pregnancy. Sometimes you'll want to do prediction inside the pregnancy, sometimes you want to start the prediction outside the pregnancy. And this is how you can kind of change your time at risk settings. But you can also make your tar end date relative to the end. So now our end date is relative to the end of the target, but our start date is relative to the start of the target. So here you've got a nice big tar. This is getting the biggest tar. And then finally, you can make everything relative to the end period. So this is very key. The exposure days to start is because we're trying to be consistent with PLE, and exposure tends to be drugs that PLE do. So we wanted to keep the same names for the population settings. But exposure it's not necessarily exposure to a drug. It's just saying the end of the target cohort. And then you have some other information like the minimum tar. So you might specify in your cohort that you want at least 365 days post-observation, prior observation when you do your prediction, because that's what you want to use to construct your features. But when you're actually looking at your model, you might want to say, well, what if I extended it to say at least they have to have 2 years of prior observation? So then I've got more information for their covariates. You can add that in just to see what impact that has on the model performance. And that's put there. Oh, sorry, no, this is minimum days, sorry. This is minimum days at tar. So this is the minimum, okay, so this specifies whether so with your tar, normally you'll have like a year's worth of observation. This is specifying whether you want people to definitely have that tar. So if someone starts in their cohort and your time at risk is 1 year, but they leave 6 months into that and they haven't had the outcome, you don't know whether there's someone who would have had the outcome after 6 months to the end of tar, but they just left before they had it. So it might be that they might have died before they would have had some outcome. So sometimes this is just basically adding noise to your data, and then we don't really know the best situation with this. But generally, if they leave and they're someone who didn't have the outcome, you want to a lot of the time you'll want to get rid of them because you don't know whether they would have had it. But if they have the outcome and then they leave, you know they've had the outcome. They can't not have the outcome once they've had it. So you pretty still want them in there. So you can actually, so the default is to keep all the outcomes, but people who didn't have the outcome, they leave, you get rid of them. But you might want to do a sensitivity and be like, okay, if I get rid of that and actually treat everyone equally, and if you have the outcome or not, you're removed. Then you can actually set this should subjects with exposure be contained to no rather than yes. And that will actually then tell you whether you potentially added a bias by keeping the outcome people but not the non-outcomes who didn't have complete tar. And sometimes you might want more prior observation. This is what I was talking about in the earlier one. So if you want the more prior observation, you can set that in this option here. And you might see if I added more observation, will my prediction get better? Sometimes you might have people for multiple times. This is what was mentioned earlier. You might have people in your cohort that are in there multiple times, but you only want the first time they're in the cohort. So you can say, make sure that the first exposure is to be included is yes. And then have a min time at risk, but the outcome causes death, maybe include outcomes who leave tar. So this is where you can actually set this to yes or no and see what the impact is of removing people who didn't have the complete tar. And if you want people who have never had the outcome before, So sometimes it might be you want to be clean and say, I want to do a prediction where you've never had the outcome. So in people, I'm predicting the first time outcome, you can actually say, remove people who have the outcome in this point. Sometimes a lot of the times the outcome is very predictive in a model. So Chads, I think they actually have it. They keep it. So you might want to actually ignore this and keep the outcome people in there. So. And then you have lots of other settings. So the execution settings are when you're actually doing it, do you want to add a sample? Sometimes if you've got very big data, then it's going to be very slow to train. So you might want to sample. So if you had 2 million people in your cohort and you didn't want to spend 2 hours or so, or however long it's going to take to train it, you can actually say perform sample yes, and then you can specify how many people you want to sample just to speed things up. See if it's a feasible prediction. If it is, maybe then put everyone in there and repeat the process. You'll also have an option for minimum covariate fraction. So if a covariate is very rare, then it's just going to mean that you've got space in your computer being used up for the actual keeping it. Your data set's going to be much bigger, keeping all the features. And it's probably not going to be predictive if it's very rare. It's probably not going to be useful if it's very rare. So you can actually get rid of it. But it depends. If you've got a very rare outcome, then you might want to keep things that are very rare because maybe they would be predictive. So you can specify this minimum covariate settings, and it all depends really on the situation when you're applying the model. And then normalized covariates. So normally we suggest normalizing the covariates. A lot of the models actually require the normalization to get some nice convergence. Like Lasso has issues if you turn this off, Lasso logistic regression. So, but it might be for some models you don't want to normalize, or you might have your own custom model where you do some normalization yourself. And then the training settings is how you're doing your holdout set. So are you doing a person or a time holdout? What percentage do you want to do for your holdout? So the default is 25, but you can set that to anything. If you had small data, perhaps you'd want to make that bigger just to see you've got less variability in the performance, but you might also want to make it smaller so you have more data to train on. So this all depends on the situation you're in. The number of folds when you do your hyperparameter selection. The default is 3 because I'm assuming there's lots of data, and the more folds you do, the longer it's going to take to train. But if you have big data, do 3. If you have small data, you probably want to increase your fold size. And then the last bit is a seed. So if you want to make it so that you can reproduce the same results next time, set the seed. If you're not too bothered, you can ignore the seed. You will get told the seed. It will be in the output of the object once you trained it. If you don't put it, it will tell you which one was the step one. And then when you're actually running a model, the things that you're going to need to specify is, first, the important one is fftemp directory. So this is the location where all of your data gets saved. We have such big data, it can't actually fit into R, because R does everything in memory. So a lot of the times, R would just say fail if you try to do it normally. So we actually create objects that are FF objects, and they go into the fftemp directory. So you need to specify a directory where you have read and write access to put the data. And then you need to specify an output folder where you want to save your results. And then you just need to put in your database connection details. So this is actually executing a package once you've used Atlas. And then once you put in your database details, you can then just press source on R, and it will do the training, it will do the evaluation, and you'll get all your results out. And it will also create a validation package for you. So I've kind of avoided the R too much, and we've talked more about the Atlas. But Atlas is effectively just calling these R functions. So we're creating a package that has a standard skeleton structure that calls these R functions. So if you wanted to manually do stuff rather than using Atlas, then for each of these different steps in the process of developing a model, you would use these functions. So I said create cohorts in Atlas because Atlas is so nice to create cohorts. It's quick. You could actually use SQL yourself manually. And for the database connection, you've got create connection details. For selecting the predictors, you've got create covariate settings, extract data, get PLP data, get study population for the population. The select model, you've got lots of different models. The way we standardize it is that it's always set and then the classifier's name. So set random forest, set gradient boosting, set logistic regression. You can have lots of different models there which you can play around with. Run PLP then actually, once you've got your data and you specified all of your models that you want to run and the settings, you can do run PLP that will then train your model, evaluate it, and you'll get the object which I'm about to show you output from it. And then there's also a function external validate PLP. So assuming you have access to some more data sets, you can use external validation of external validate PLP to validate your model on the other data sets that you have available. If you don't have access to other data, I recommend putting it on GitHub and asking the community to run. So examples of all this R code is online. There's actually a vignette that contains very detailed instructions for all of this. It's on the README on our GitHub package, but you can also find it in this link. And it really has very extensive details. We have other vignettes on the README as well for all the different processes that we have, like the deep learning, the ensemble learning. If you want to do the multiple PLP running, they're all on there. And Peter's made them very nice recently. So the models and parameters, this is, as I was mentioning, the structure we use is the set and then the model name. Set lasso logistic regression, set gradient boosting, set random forest, and here's all the hyperparameters. I believe this is in the vignette. So if you go to the vignette, you can actually see all the different settings that we have. We didn't put everything that you could put in for some of the models, and this is actually something, if there is something that you want added, so if you were running this and you wanted a hyperparameter added in, you could always tell us on the GitHub issues, and we could add that in, or you could do it, submit it to GitHub, and we'd, as a push request, and then we'd pull that in. And then this is like some of the more recent models that we've added. So this is a new slide for this year. So we've added in a lot of the deep learning models and ensemble. So we've actually got a lot of nice deep learning in there. We've got recurrent neural networks. We've got convolutional neural networks, just your standard deep net. And these have a lot of hyperparameters. So I didn't actually explain what they do because it was going to take up too many tables. So any questions at this point?
How have you tended to operationalize these models then? Like, do you have like a suggested API that you wrap the model up in, or does it spit something out like that? Or, you know, presumably the system you're interacting with isn't running R.
Yeah, so it's all like an R interface. So you'll have some R interface that says, assuming we have the data, the PLP data in this structure, the population in this structure, and some other settings. So like that you would assume that you've got some settings that you'll be using for your models. Then you would just say now like interact and do whatever you want. So it could be running some R function. It could be interacting with Python. We have a Python and R interaction. It could be doing any other like algorithm that you can, as long as it can interact with R. So R just says call this function or do something, and it outputs the format you need then for the evaluation. You can plug anything in. So you just have to assume that you've got the set format and there's a set output, and whatever happens in between, you can just do whatever you want. We have algorithms in Java, Python, C, lots of different languages. I think there's a vignette as well that might explain. I think there's a vignette that says adding novel methods that will kind of explain what's needed, and it probably needs a bit more details about some of the inputs and the outputs of it.
Yeah, so maybe to follow up on that issue, there's so many parameters you can set. So I like your format that it's relatively easy to modify things, but say the advice on default settings, etc. Is that in the vignette basically?
So for the default hyperparameter settings.
Yeah, that sort of thing. Yeah.
Yeah. So I think in the vignette, did we say the defaults?
Yeah, so there are different options then. So that we come to that in a later session on the reporting. So I think it's really, really crucial that to be very specific on the choices were made. So if I may highlight one thing that I struggle with is this outcome definition that you mentioned, the time frame you consider. So this concept of competing risks by dying from another cause, which precludes occurrence of the event you are interested in. Is there any option to deal with that in
Yes, that's a great question. So this is an area really we definitely need some work on. So there isn't, if you know that someone's likely to die from the outcome you're predicting, right now all you can do is say use all outcomes, no matter if they leave during their time at risk. But then you're like, if I don't do the same option for the people who don't have the outcome, I've got a bias because I'm getting people who could have died in my outcome, but they definitely didn't die in my non-outcome. So you've got issues there. But if you say to use them, then you've got noise because if someone's a 0 and they leave it halfway through their time at risk, you don't know if they would have been a 1 in the continuation. So then you have the bias of that's noisy labels, potentially. So we don't have any good solution for this at the moment. If you know of anything for... Okay.
After building the model, and then do you have query function? So after building the model, can we put one patient information and then find out the results?
So in R, once you've built the model, you can look at I should be showing in the next few slides, you get a prediction for all of your target population. So it's the same as you get for your target. So you'll have a person, their target start, their target end, and some other information about their observation. And then you'll have a predicted risk at the end. So you can look at, for one person, what their risk was. And then in Atlas, there is a person viewer. So you can take the ID for that person for your database, go into Atlas, put it on, and you can see their whole timeline. So sometimes I will, if I look at a model and I'm like looking at someone that seems to have something weird that was unexpected, I'll look at them in Atlas to see why they were predicted high, or why they predicted high but they didn't have the outcome.
Question: you have really nice shiny application for presenting results of package run, but I'm pretty sure I haven't seen the list of the covariates which were associated for the model, which play the biggest role in the model. Is there a reason for not displaying them, or can this be introduced in upcoming versions? Oh,
so in the Shiny app, the models that were selected, whether they're displayed, is that?
So you display the covariates prevalence in the cohorts in the person which had outcome and who didn't have outcome, but the weights of the covariates in the final model, those are not listed. Like this covariate has this 1.5 weights, the next one 1.4, and so on.
Yeah. So yes, that's a good point. So when you look at it in the individual, like so we've got 2 shinies now, which I'll be showing at some point. So one is for a single model, and that doesn't contain the coefficients or the variable importance. The reason we did that is just because we wanted to have the Shiny app for people who didn't necessarily do the modeling but were just looking at the results. And we were afraid that if we put the coefficients in, they might interpret it incorrectly. So as Peter was saying, because of the collinearity, because we're throwing everything in, the actual sign of the covariate, or the coefficient, is not always informative. You can have a minus just because it's collinear or something else. So we didn't want to put that in where there might be people who wouldn't be able to interpret this correctly. So we actually hid it. But you can see it if you're developing a model. You can go and you can actually look at it yourself in R. In the multi-PLP, I think we might have it in there just because we've been inconsistent. I've been inconsistent. But I don't know whether it is good to have in there or not. I like to see it, so it's nice.
I believe Peter has mentioned that after looking at properties of your model, you see the charts and so on, you might be interested in looking at these covariates, which are playing the biggest role in the model. That's why, for me, it would make a lot of sense to add it there, because this one, the second most important thing in the results is, I believe.
Yeah, so another thing, so we do have whether it's included, but just not the variable importance. But for most, other than Lasso, actually, it should be okay to put the variable importance in, because they are actually looking at the impact in the performance. The Lasso coefficients, don't necessarily correspond to the importance, so we need to create a variable importance for Lasso, and then I think it should solve the issues that we're having with that measurement, and we can put it in. But right now, it's just the Lasso messes it a little bit, because if people interpret the coefficient, they might interpret it incorrectly.
Thanks.
question about using the atlas to create the cohort. I might miss that point. So because for a prediction model, interpretation is a big disadvantage. It's very hard to interpret it because, especially here, as Peter mentioned, we are doing the data-driven prediction, right? So my question is, in your atlas, when I create my cohort, is there any like you store in the variables in some big bucket, like a demo, like a treatment, like clinical, like such very big bucket. And then when I choose this variable, I already know, okay, I want the treatment, right? And I can, so after I get the model, I know those variables selected are from this big bucket, and I can interpret, at least using this big category to the clinician. So do you have such functions in your atlas?
So to see the general domain of a concept.
We do have a really term for covariates.
Yeah, how in your CDM, how do you store your variable? You just list like 90,000 variables, right? And treat them, have you categorized them into
Cardiovascular disease and concepts for
or even bigger, more general category, like demographic, like
yes.
Treatment. So I don't know.
So we do group. So this in terms of grouping, we group with hierarchy using the vocab hierarchy. So there is available to us. There is a database that says this concept ID has these children that are basically related to it, but more specific. And we do actually group up. So if for this variable we say, did they have any of these children? If they did, there are 1, otherwise there are 0. So we do grouping of concepts in there for drugs and conditions. But we don't do it for procedures, observations, or measurements.
So following on that, you create indicator variables for every drug and every condition if you check those boxes. Is that right?
Yeah, there is actually another option. It was above, I didn't actually show, where you can exclude and include. So you can say, I don't want to include these concept IDs, or I only want to include these concept IDs as well. So you have some flexibility. If you wanted a model that had 20 variables, you could put in those 20 variables and just restrict to them.
And then if you select different time periods, then you'll have maybe multiple indicators for the same drug or the same condition just over different time periods.
Yeah.
Okay.
Yeah. But if you were worried about things like overlapping stuff, you could pick it. So actually no. So they would actually overlap on some of them. You can't. The end date is fixed for every single setting. So it's only the kind of start for the short, the medium term that you can play around with.
Okay.
I want to ask 2 questions. What kind of I understand what are the hardware requirement to set up those systems? The second question is what kind of model we can use to do the model select or future selections?
Okay, so in terms of the hardware, that depends on the data you have and the settings.
We have 10 million patients in our hospitals.
Okay, so generally, if you've got 10 million patients, when you restrict to your T, you'll probably not have it too big. So I would guess maybe maximum T might be like 1 million. So in that case, it would, with the system I have, so 100 gigs of RAM and CPU, most of the models would perform in a reasonable amount of time for that. But it really depends on how fast you want it.
Do we have some documentation available so that we can have IT support to provide those hardware for us?
So we haven't. I'm afraid we haven't looked at. Did you have any thoughts on computational like hardware? Yeah, so but the Amazon environment that you have been using, that would actually be one solution. That it should be like it's the cloud, so you can make it as big or small as you want. So that's one. Oh, Patrick.
But I'll just add. So there's 2 different compute environments that you're going to have. One is the database server, where your data is going to store, because that's where we do like the extraction of the cohorts and the feature extraction. So that won't be as fast as that database server. But then when we talk about running the package, everybody has a nice environment. but I'll tell you, like, I run this thing on my laptop. I run the package you're using. I run it on my laptop on massive data, and it runs in minutes, sometimes hours. So like, yeah, this is just a generic company issued laptop, and I'm running models with a target cohort of 1 million patients. It may take a few hours to run, but this is nothing special.
So apparently, just for time, I'm just going to do the next few slides. We're stopping at 12:30, is it?
12, so we need to.
Oh, at 12. Okay, so should I just do a demo? I can just go through the next ones in the demo, I guess.
Yeah.
So this is the training environment you have in Amazon. So you're all given a piece of paper this morning with instructions on it. Should have given you a number at the bottom right-hand corner on the agenda. So that's going to be your user. So the number you're given is X. So you're going to be, your username will be user followed by the number you're given. And your password is password1 with a capital P. And you can go to this. This will be left up for a minute, so you have plenty of time to copy this down. And then once you're in the R session, you'll also have a folder that has some documents, including the vignette for running some of the functions.